Okay, so question 3 was about ideal gases. And the first one, we were basically being asked to estimate the average speed of the gas in the container. So we wanted to work out the velocity. So we know that kinetic energy can be given by the equation half A equals mv squared. And for ideal gases, it can also relate to their temperature by 3/2 kT, with K being the Boltzmann constant. In this case, I simply rearranged for velocity. So velocity was equal to √3 kT divided by m. And then I simply sub in my values. So Boltzmann constant you get from your data booklets, 1.38 times 10 to the minus 23. Temperature should be in Kelvin, so 320, which is fine. And the mass, which I got up here, so again came down to be 1,416.7. Again, trying to give my questions two significant figures because my question was using two significant figures. So 1.4 times 10 to the 3 meters per second. For part B, it was then showing the number of helium atoms. Number of helium atoms, okay, is big N. It's not the number of moles. But I can use PV equals nRT to calculate the number of moles, and then I can use the number of moles in Avogadro's to find the number of molecules, or number of atoms in this case. Okay, so simply with N, I'm going to use PV divided by RT. Again, just plugging in the values that I've got from above. So to give me 0.0061, and I left that full and I left it in my calculator. To work out the number of molecules then, we did the number of moles multiplied by Avogadro's constant. Avogadro's constant is given to you in the data booklet, and it's 6.02 times 10 to the 23, so I just multiplied that by my answer from before to give me 3.7 times 10 to the 20, okay, which is approximately 4 times 10 to the 20 number of atoms, okay, and it's asking me to show that up there, so I'm still going to just show that at the bottom. So rather than just leaving it like this, I always want to put in that little bit there. The next part was then asking you to calculate the ratio. Okay, so it's telling you one helium atom has a volume of 4.9 times 10 to the minus 31. It's asking you to calculate the ratio of the volume of helium atoms compared to the volume of helium gas. Okay, so what I needed to do here was I multiply my volume of one atom by my number of atoms, and I used the 4 times 10 to the 20 that I'd got earlier. You could also use that 3.7 as well, but I chose to use the answer that they'd given me rather than my calculated version, and that's a bit of a tip. I would tend to do that anyway. Divided by the volume of helium gas. Again, my volume of gas was all the way from before. And in this case, that gave me 0.006125, which is 6 times 10 to the minus 5. And it's a ratio, so there's no units. But I'm going to use that answer later because it then says in part D that I need to use it for above. So it says, discuss by reference the kinetic model of the ideal gas and the answer to CI whether the assumption that helium behaves as an ideal gas is justified. So here we get to look at our assumptions of an ideal gas. And so you could basically have said that for an ideal gas, we assume the particles are point objects, okay? Or you can rephrase it and say it in the way that volume of the particles is negligible compared to the size of the gas volume. Essentially, the volume of one of the atoms, okay, all of them added together, that volume that it occupies is actually so much smaller than the volume of the gas itself. You could also have said here that the volume of the gas would be much greater because the distance between the particles would be bigger than the volume of the particles. That's another way that you could have phrased this, but it's not as nice to phrase it like that. So I've kind of said what my ideal gas law is. That gives me 1 mark of it. My second mark comes from then linking it back up to my part C up here. So I said the ratio shows that the volume of the helium atoms is much smaller than the volume of the gas, so it is justified. Okay, again, if we're showing here, 6 times 10 to the minus 5 times smaller is the volume of those helium atoms. So I get 1 mark for linking to the assumption, and then 1 mark for my justification of the answer there. All right, so 1 mark for each. And that was question 3.